This is lesson 10.3, which is all about vectors. Our essential question is, how does including a direction with a quantity affect how you carry out operations on quantities? So a vector is written as a letter with a little arrow above it. It's a quantity that has both a direction and a magnitude. So the direction of the vector, we start with an initial point and we end at a terminal point. It's kind of confusing because we think about in geometry with ray has an arrow at the end and it looks similar to a vector, and that keeps going on forever. But even though there is an arrow at the end of the vector, it's just showing us the direction of the vector and not that the vector continues on. So we have a starting point, an ending point, and then the arrow shows us which direction the vector is headed. The other part we have with a vector is the magnitude, and that is just telling us how long the vector is. So our first example says a plane is flying due north but is pushed off course by a crosswind blowing east. At 1 p.m. the plane is at the point 1010, and at 2 p.m. the plane is at the point 100-410. So we want to find the speed of the wind and the speed of the plane due to its engine. How can you represent the change in the plane's location? It's a vector written in component and matrix form. So component form is going to have these triangular brackets, and we have our x distance and our y distance. So if we're looking at this example, if we start with 1010 and we go to 100-410, for moving in the x direction, we moved from 10 to 100, which would be 90. And moving in the y direction, we went from 10 to 410, which is 400. So that's component form. And then it asks us for matrix form. So matrix form is just like the matrices we've been talking about. We're going to put the x distance on the top and the y distance on the bottom. So then part B says, how can you describe the direction the plane is heading? How fast is the plane moving with respect to the ground? So if we're trying to find that little angle in there, we're going to use tangent, inverse tangent, and we know that this distance is 90 and this distance is 400. So we can set up our equation. We can say inverse tangent of 90, opposite, over adjacent, 400. And if we type that into our calculator, we get 12.7 degrees. So that tells us that the direction of the vector would be 12.7 degrees. And then the last thing is, how fast is the plane moving with respect to the ground? That's going to be the magnitude. So we're going to find the magnitude of vector AC. And to find the magnitude of a vector, it's kind of like, it's just the distance formula is all it is. So distance formula, or you can think Pythagorean theorem. So we're finding the square root of our x distance squared. So our x distance was 90, so 90 squared, plus our y distance squared, so 400 squared. And so if we take that in our calculator, we get 410 miles per hour. Okay, so example 2 says, how can you add vectors? There's some typo thing in here. Ignore that. 4, 8, and 3, -6 graphically and algebraically. So I'm going to use some colors. So let's make vector v 4, 8. So I'm going to start at the origin, and I'm going to go 4 in the x direction and 8 in the y direction. So that's not a perfect vector, but there's my vector v at 4, 8. Now to get vector, let's do blue, to get vector w, I could also graph that starting at the origin and going 3 and back -6. But when we're adding vectors together, we are thinking head to tail. So we're thinking kind of a path. So we have our vector v, the red vector that I just drew. And now from the ending of that vector, we're going to add on vector w, which is going 3 to the right and down 6. So that would put me right there. So this is vector W. This is vector V. And then to find the addition of them, we're going to start from the origin. And we're going to end, so this would be V plus W. So then we can double check our picture algebraically. So if I were to take 4/8 plus 3 negative 6, if I add the x components, I get 7. And if I add the y components, I get 2. And if you look at my graph over here, vector v plus w ends at the point 7, 2. So we can algebraically add vectors, but we can also show with the graph. Okay. Example 3 says, Paige is operating a boat across the river with an engine speed set at 12 miles per hour, headed 30 degrees south of east. The current of the river is 2 miles per hour at a direction that is 30 degrees west of south. What are the magnitude and direction of the path of her boat as she operates it across the river? Okay, so the first thing we need to look at is we need to get the vector for Paige and her boat. So if you look at the little picture off to the side, the orange vector E is representing the boat, and the blue vector C is representing the current. So if we start with vector E, we need to find in component form what that vector would be. So to take the information that we have to find the component form, we're going to take the magnitude times the direction. So we would take 12 cosine of negative 30 and 12 sine of negative 30. And so if we type that into our calculator, we end up with 10.39 negative 6. So that is our vector E. Then we need to find vector C, which is our current. So for that, we're going to take 2 times cosine of 60. So the reason we're saying 60 is because we don't usually talk about the angle that it makes with the y-axis. We talk about this angle right here. So our reference angle is going to be 60 degrees. So we're taking 2 cosine of 60 and 2 sine of 60. So that gives us -1 and -1.73. Okay, so once we have our two vectors, we are adding them together to find the result. So you can think of her boat on that orange path is getting pushed back this way, and then we're finding the resultant vector right there. So that's just kind of a sketch of what we're actually trying to find. So we'll call that R. So that's our resultant vector. So our resultant vector is going to be vector E plus vector C. And so if we add those together, we get 9.39 and -7.73. So it wants to know magnitude and direction. So we have the component form, so now we can find both the magnitude and the direction. So the magnitude of vector R, we're going to do the square root of 9.39 squared plus -7.73 squared. Notice I'm putting parentheses around those. That's important because sometimes if we forget those parentheses and we type the negative in our calculator doesn't calculate it correctly. So for our magnitude, we're getting 12.2. And then our final step is to find that direction. So we're going to take the inverse tangent of our y value over our x value. And so I'm going to take the 7.73 over 9.39. And we're just trying to find that angle right there. So I'm leaving it to be a positive 7.73 because we're going to do the inverse tangent and we're just trying to find that reference angle. So if we do that, we get 39.5. So that would be our angle, and this would be our magnitude. Okay, our second to last example. Example 4, understanding vector subtraction. So this picture already kind of shows what vector subtraction is, but it says, how can you subtract v minus w graphically and algebraically when v is 6, 2 and w is 0, negative 4? So you can see v is the blue vector right here, and w is the orange vector right here. So if we're taking vector v minus vector w, another way of thinking about that is to just take vector v plus negative vector w. So negative vector w would be just moving it in the opposite direction but the same magnitude. So you can see what that is that's actually, let's erase this here. This is taking vector w, and see how that purple dashed vector is the opposite direction of vector w, and it's going to be added on to vector v. So if we take v plus the opposite of vector w, then that allows us to find v minus w, which is that orange solid vector right there. So if we were doing that, if we look at, we can confirm on the graph. So the graph gives us 6, 6. But if we look up here with our numbers, we can take 6, 2 minus 0, negative 4. So if we algebraically do that, 6 minus 0 is 6, and 2 minus a negative 4 is actually plus 4, so we give us 6. So you can see those match. Okay. Oops. Let's erase that. Okay, this is our last one. Okay, so multiply each vector by the given scalar. How do the magnitude and direction of the product compare to the original vector? So you can see these are graphs of each of these vectors multiplied by the scalar. So the scalar is just telling us that we are scaling that vector 5 times bigger than it originally is. So if I have vector r, which is 9, 3, and I multiply it by the scalar of 5, I'm going to end up with 45, 15. And so you can see that this should have an arrow at the end, but this right here is our scaled vector. So the blue dot shows the original vector 9, 3, and then we're just scaling it 5 times as big. It's still in the same direction. Okay, part B says that we're going to scale vector 4, 5, and we're scaling it negative 3. So that means the negative tells us we're going to be changing direction 180 degrees in the opposite direction, and we're multiplying it by 3. So that's going to give us negative 12, negative 15. So you can see that's where this vector ends up right there. Here's our original vector S.